Hi, in this recording, I want to discuss elastic collisions in pi space. In classical physics, you have two objects colliding, and essentially the total energy is conserved and the total momentum is conserved. It's um, it's modeled in the physics with the following formula. You have the conservation of momentum here, and you have the conservation of energy, and then what you do is you have the kind of the before velocity and the after velocity, and the before energy and the after energy, which matches the velocities in this case change. In this case, I've modeled them as v3 and v4, v1, v2 before, and v3 and v4 after. In a lot of cases, some people use a dash. They might say v1 and then v1 dash for after, and v2 dash for after, or v1 and then v1 final for after, and so on. I'm just using v3 and v4 as the after values. It doesn't change the calculation, but it's just the notation I use. So this is the classical elastic collision formula, and you get the final value here, which is v3 in our case, and the final value here, which is v4 in our case, in the formulas I use. And it's pretty standard stuff. You can look it up. This is well figured out already. Now, what we're going to do is just implement this solution in pi space, which is the physics theory. So the idea is that we want to conserve energy. We already have a kinetic energy formula here, which is already established in the theory, and so we want to conserve it. So we have the 1 minus the cos arc sine times c squared. So this is the Newtonian analog of kinetic energy in pi space times the mass. So this expression here is the two object 1, object 2 before, object 1 and object 2 after, and they're conserved. I do a little bit of work on the math, and I talk about the momentum, which is always conserved. So I use a mathematical notation here where I have the momentum here before and after, and we want to solve for v4, and the idea is that v4 then gets replaced back into the overall formula, and we want to solve in this case for v3, which is v1 final. So this is the mathematical expression here, which you can see. It's if you know mathematics, you'll know this notation. So basically we solve for it and we get this rather large expression here, which is the solution in pi space for the v3, which is v1 final. And then we can do the same thing for v4. We take the overall expression and we substitute back in for v3 the v1 and v2 equivalent, and we solve for v4, and we get this rather large expression here. And that's it. That's how it's done in pi space. So worked example. We have the one I've used for the documentation. I'll show the software in a minute. Is ball 1 and ball 2 collide, and they're 3 kilograms and 4 meters per second, 5 kilograms and minus 6 meters per second. The assumption is that they collide exactly the same at the same point with one another. Then I also work out how to do that at an angle, but for the purposes of this lecture, we assume they just collide head on with no offset angle, just straight on. So if in the documentation, the document that I'm referring to here is called the momentum interaction diagrams. It's available on the physics site that I have. You can search for it if you can't find it. So this is the example here. You put 3, 4, 5, and 6, and you put in the values, and it gives you back 8.5, which matches the classic formula. Now this is a fairly, I could imagine one would prefer not to use this formula if one uses the classical formula, because obviously it's a lot of work to implement it. Um, the benefit, of course, according to the pi space theory, is this formula works for high velocities, not just for these smaller velocities. So what I've done is I've implemented, if you've been following the lectures, I've implemented a test class in the SourceForge documentation. It's called Test Pi Space Elastic Collision, and I have a series of tests that one can run where the methods are called in a variety of situations. So I test elastic collisions using the Newtonian formula with the pi space formula, and if you check out the code on the SourceForge using the Git repository at the time of writing, that's how it's implemented. You get the correct values back. I also have a test example for a very high speed, a fraction of the speed of light, and that's the idea of it. So if I just delve into a test example here, I construct the class, I pass in the values here, and then I call it the method, which is the Newtonian version of the method. I pass in pairs v1 and v2, mass 1, velocity 1, mass 2, velocity 2, and I check the predicted result, which is minus 8.5, against the Newtonian one, and I get 8.5. And this is using this is the classic formula that you'd get on the internet if you searched on most major physics websites. And then I test v2, and then I also test the pi space one. So I use the pi space one here, and they match. If you look at the implementation of the code, I've had to use a big decimal to use it, to do it. The only small difference between the two formulas is that if you use the pi space formula, you'll notice that if you have two objects and they are exactly the same mass and velocity colliding with each other, the result that you get back is 0. So in other words, there's zero exchange of energy between the two in terms of there's no differential. So the way it works in pi space is that the way the code works is, if you get a 0 result, you basically get the two objects repelling from one another. So in other words, you just minus each of them. So if one is going in with v1 velocity and the other is going in with v2 velocity, and they're equal, and the mass is equal, then they just switch each other's masses and velocities. In other words, they bounce straight off each other, and that's probably the main difference between the formulas. The values you get otherwise are pretty much the same at the smaller ranges. You know, the 20 miles an hour or whatever, 50. When you go up to 0.5, 0.6 speed of light, whatever, the two formulas diverge quite a lot. I mean, the Newtonian one isn't relativistic. I know there is a relativistic version of this formula online, but the one I tested against was actually the Newtonian one. So the final one that I have in the test suite is the large velocities. So I test with 0.7 and 0.8 of the speed of light. So these are the values that pi space returns. And the idea with the pi space formulas is that you never get a value greater than the speed of light, which is sort of the Einstein approach. And that's the way the elastic collisions work out. In another lecture, I may talk about how I've done this one here, the elastic collisions at an angle. So basically, I also calculate what the results should be if there's a collision at an angle, instead of when they collide straight on, and what the extra steps that need to be done there. Thanks very much. Bye now.